Okay, once again, good evening, students. Uh, Today we are going to discuss the most important class of the second unit, that is signal conditioning. So, the topic of today's talk is A to D and D to A converters, right? So, first let us understand what are these devices and why we need these devices. So, your A to D or ADC is basically an analog to digital converter, whereas DAC generally people termed as DAC or D oblique A, that is digital to analog converter. So today we'll be going to discuss these two important converters, right? So your first converter, as the name suggests, it converts your analog signal into digital one, whereas the D2A converter has a reverse process, that is, it convert digital signal into the analog signal, right? In our day-to-day life, uh, we are using these kind of converters, right? The most important example I have written here is a sound pickup by a microphone, right? सभी लोग हम लोग काम में लेते हैं, and a light entering into a digital camera, right? So it is nothing but your analog to digital conversion, right? And in while we are talking on mobile phones, both type of converters are happening, right? So in our subsequent slides we'll see how these conversions takes place and why we need this conversion, right? So let us see the next part. In this slide I have shown a pictorial representation of how a digital signal is converted into the analog, sorry, how an analog signal is converted into the digital signal, right? So here you can see in left hand side, this is an analog signal, and we have used a converter, that is ADC, analog to digital conversion, and in the output side we are getting a digital signal. Okay, in case of digital to analog converter, we are inputting is a digital signal, right? And we are using a device DAC, that is digital to analog conversion, and in the output side we are getting an analog signal, right? So in the nutshell, in ADC, our analog signal is converted into a digital form, whereas in DAC, our digital signal is converted into the analog form, right? So the question arises, what is the need of these kind of converters? Okay, so first let us see what is the requirement of such kind of convergence in our day-to-day life. So as you all know that the most of the physical signals like temperature, pressure, sound, all these signals that we came across are analog in nature, right? But at the same time we all know that most of the instruments and equipment which are used nowadays are based on digital technologies, right? Digital technologies means these instruments deals with only the digital signals. There are the instruments, they only deal with the analog signals. So in both the way we need some kind of conversion. Okay, so first we'll see the A to D converters, right? We all know that our analog signal is susceptible to noise, right? And it is very difficult to process, and also it is difficult to store in analog domain. Whereas if we talk about the digital signal, then they are less susceptible to the noise, they are easy to process, and also in digital domain they can be easily stored. Okay, so now first we'll see how A to D converter works. So the very important example of an A to D converter is LM339N, right? It is nothing but your analog comparator, right? So let us try to understand. This is an comparator, right? There are two inputs. One is reference input and one is in V in. V in is your nothing but your analog signal, right? And in the output side, we are getting a logic output. Okay. So suppose our reference input, that is analog signal, is 5 volt. Okay. And this input is going to be changed. So the concept is, if your input is 2.5 volt, which is less than this reference, then your logic will be, output will be 0. And when this V input is equal to 5 volt, then only we will be getting 1. So in this way we can say that when input voltage is equal to the reference voltage, then our logic output will be 1, whereas when the input signal is not equal to V reference, then our logic output would be 0. So in this way, here the analog signal is converted into the digitized form, right? That is binary coding. Okay, but in this conversion, uh, some information gets lost, because we all know that the analog signal is continuous in time as well as continuous in amplitude. It means if we see the analog signal, right, then this is our analog signal, and at every instant of time we are getting some values, right? So theoretically we can say that an analog signal has infinite resolution. At every instant of time we are getting some value, right? The value may be different, so we are getting a number of values at different time span. Okay, so in this conversion some information gets uh, lost, right? So how we can recover the exact information at the receiving side? So let us try to understand. So before going to discuss, the very first process is to convert an analog signal into the electrical signal with the help of electrical transducers, right? We have already discussed this chapter. Electrical transducer is basically a device which converts a non-electrical signal into the electrical signal, right? Here we have electrical signal in our output side, okay, but still this electrical signal is in analog form, right? And we want to convert this analog signal into the digital one, right? So ADC means analog to digital conversion follows a sequence of steps, right? While converting this analog signal into the digital signal, the first, ये आपको बहुत इंपॉर्टेंट चीज है, इसको आप समझिएगा। यहाँ पर तीन बहुत ही इंपॉर्टेंट प्रोसेस आने वाले हैं, ठीक है ना? इसको पहले इसको देखिए। द फर्स्ट इज सैंपल द सिग्नल, राइट? Sample the signal means here a process is used that is known as sampling, right? Then the sampled quantity, it quantify it to the it to determine the resolution of the signal. Here a second process comes into the picture that is known as quantization, and finally the quantized signal is coded into binary values, and then this signal is sent to the system where it has been read, right? So in A to D conversion there are sequence of steps involved. The first step is sampling, the second step is quantization, and third step is coding. So let us try to understand one by one these processes. Here I have written three processes. So this one is your sampling. Sampling means we are getting the samples of the input signal that is analog in nature, right? And in the quantization process, we are having certain values rather than infinite values. I will discuss this point, how this quantization takes place. And in the final steps, this quantized signal is converted into the digital or binary coded with the help of encoding. So what we have understood is in A to D conversion, there are three steps. One is sampling. Sampling is to convert the analog signal into the digital, nothing but the samples, right? Here quantization means to convert infinite amplitude values, right? Infinite amplitude values means we know that the analog signal having infinite values at different times, right? It is continuous in nature, so theoretically it has infinite resolutions. So in quantization process, these infinite amplitude values are converted into finite values, right? It means the sampled signal is assigned to a particular value. In our next slide we will see this process in detail, right? Whereas the last process, we are using encoder that converts these fixed number of amplitude means the quantized signal into the binary digits, right? So let us try to understand first the sampling. This blue color continuous wave is showing your analog signal, whereas these samples are basically the sampling process, right? So in sampling, the analog signal is converted into samples, and this process is done at a particular rate. Please take a note of that, right? Because in order to decide the sampling rate, we make use of a theorem that is known as sampling theorem, right? And most important thing is, if we are using more sample, then at the output side we can represent it more accurately. Okay, so what is this theorem? Let us try to understand. Actually, this theorem is given by Nyquist, and this theorem says that the sampling rate should be at least 2 times of the maximum frequency of the input signal, right? And uh, in our next class, we will discuss this theorem, derivation of this theorem, uh, and why this theorem is used. The main purpose of this theorem is to recover the signal at the output side in a proper format. So for the time being, please take a note of that. The sampling frequency, it must be greater or equal to, sorry, I have mentioned 2 is miss here. So please note that this is 2 times of FM. FM is the maximum sampling frequency, right? Now come to the quantization process. In quantization process, the sampled signal is assigned to a particular value, and this value is known as quantized value, right? From the discrete set of values, discrete set means it may be 0, 1, 2, 3, 4, etc. And one important thing is the same magnitude is assigned with a same number. So let us try to understand what we are going to say. Here you can see that this dotted wave is nothing but your analog signal, right? And we have sampled this signal. Sometimes this signal is known as pulse amplitude signal. In the laboratory section, we have also discussed this part. So again, we are revising this portion. Here you can see that the second sample and third sample, these are very close to each other, right? So what we have done is the extra portion of this third sample is discarded, and the sample 2 and sample 3 both are assigned the same value, right? So in this way, the infinite samples are converted into finite samples just by discussing the extra portion. So the most important thing of the A to D converter is resolution. So let us try to understand what is resolution. So the resolution of ADC decides how the quantized value is close to the actual value, and this is usually defined in terms of bits. So there is some mathematics involved in this process. So let us see. Resolution का मतलब होता है number of bits, right? And number of bits means what? The number of bits in which the quantized signal is going to be encoded, right? So basically, this resolution defines the minimum change in the input signal which can be detected, okay, by A to D converter. For example, it may be 8-bit or it may be 16-bit coding. So when 8-bit coding is used and when 16-bit coding is used, it depends upon the resolution, right? So suppose we have given an A to D converter and the resolution is n-bit. Then the binary number system, the total number of discrete values that can be defined is 2 to the power n. Okay. For example, uh, if we have an input signal first, then it is simple, then we'll be getting the quantized value as 2 to the power n levels, where my resolution is n bit. Hence, the number of discrete levels will be decided by the resolution of A to D converter. So let us try to understand this concept again with the help of a numerical problem. So suppose we are having an A to D converter whose resolution is 3-bit. Okay, then how many discrete levels would be there? So it is nothing but 2 to the power n. It means 2 to the power 3, that is 8. Suppose we have an A to D converter whose resolution is 4-bit, then total number of discrete level would be 16 as 2 to the power 4. Okay, the resolution is also defined in terms of full scale range, right? and it is given by a ratio that is full scale range का मतलब होता है कि मैक्सिमम वोल्टेज रेंज जिसको आपको कन्वर्ट करना है डिजिटल में, राइट, डिवाइडेड बाय 2 to the power नंबर ऑफ बिट्स मींस योर रेजोल्यूशन। इसको भी आगे समझते हैं अपन। मान लीजिए आपके पास एक ए टू डी कन्वर्टर है जो कि 3 बिट का है, ठीक है, एंड our maximum voltage range that is to be converted into digital one is 5 volt, okay, so our resolution would be, सॉरी इसको 10 वोल्ट मान लीजिएगा आप, गलती से 5 आ गया है, सो रेजोल्यूशन वुड बी 10 by 2 to the power 3 that is 1.25 volt. So this is the minimum change in the input that can be detected by your ADC, right? And if the change in input is less than 1.25 volt, then it would not be detected, right? So let us see one more example. Suppose we have a 8-bit converter. Please read it as 10 volt rather than 5 volt. So in this case, the resolution would be 10 divided by 2 to the power 8. So in this case, our resolution has increased to 39 millivolt. Earlier, decreased. Earlier it was 1.25 volt. Now it is 39 millivolt, right? So what we have seen, by increasing the number of bits, earlier we have 3 bits. Now we have 8 bit, okay? So by increasing the number of bits, we can increase the resolution. So thanks students.